If you are an electronics engineer or a hobbyist or an enthusiast, you very well know how important a multimeter is when it comes to testing and pin identification of electronic components. But using a multimeter every time to identify the components like transistors or MOSFETs can be quite time consuming, provided you have the pin diagram of each component with you. You always wish if there were a device that could do it automatically so you could save time and effort while repairing circuits or building new projects. I recently picked one such device online which could do exactly that, and I loved it. It not only identifies components automatically, it also prints out basic component specifications that could make your job so easy. Let's see how I improved it further by building an acrylic enclosure and made it portable by adding a lithium ion power source. Now I can carry it around and not have to worry about replacing the batteries. So, without any delays, let's get started. The hardware itself is pretty bare bones. It's just a PCB with green color backlit 128 by 64 resolution graphical LCD. In addition, it's got a 14-pin ZIF socket and a push button. The whole thing is powered by 9-volt DC. You can power it using a 9-volt zinc carbon or alkaline battery. You don't have any control over the brightness of the LCD. The whole unit just goes to a low power mode after a measurement until you push the button once again. I couldn't stop getting excited when I noticed the system is based on the familiar Atmega 328P chip. Usually these Chinese boards come with some microcontroller like the STM, with or without their marking scraped off of course. So I guess there is hope for me to learn its working or to get my hands on some literature on the internet that helps me, possibly even with some firmware changes. But first, I need to make it portable and safe to carry around and to work with. Let's get on with the modifications. A quick internet search landed me to some ready-to-assemble acrylic cases for this module, but it makes it bulky. Plus, you need to unscrew it and open it every time to replace the batteries. I intend to give it a rechargeable power source, so I decided to DIY my own case out of 2 mm clear acrylic. After a lot of cutting and sanding the edges to dimension, with the help of some M3 nuts, bolts and screws, it was finally time to put the pieces together. So, after carefully aligning and measuring everything, I marked the spot for drilling the holes. Then, using acrylic glue, I attached the pieces together, and just like that, the enclosure was ready. Now the module, along with the battery, can just be slided into the enclosure and held in place with the help of 4 screws. Now that we have gotten that out of the way, it's time to build the power source. I used a spare lithium-ion battery from an old smartphone that seemed to agree perfectly with the dimensions of the board. To power the component tester from the 3.7-volt battery, I used a lithium-ion battery charger cum boost converter to step up the 3.7-volt to 9-volt DC. The module features a TC4056 standalone lithium-ion charger IC with necessary battery protection features. You can easily charge the battery with a standard USB charger. It also has LED indicators to show the charging status. The bundled boost converter can convert 3.7 volt from the battery to as high as 4.3 volt to 27 volts. However, for our mod, we just need 9 volt DC. So, we can adjust the onboard preset to get an output of 9 volt DC. I was looking for a way to fix the boost converter board onto the main PCB so that everything fits together and it's nice and compact. Luckily, the board just sat perfectly in its place, like it was designed to go there. However, I had to protect the solder pads on its underside from accidentally shorting with the SMD components of the main PCB, so I applied some Kapton tape to insulate them. Now I can use 2-part adhesive to permanently fix them together. Now it's time to wire it up and solder the connections. Before soldering the connections, I made sure to adjust the boost converter's output to about 9 volt DC. Then I soldered the DC input terminals to the positive and negative of the boost converter's output respectively. After soldering everything, it was time to check the voltages. Using a multimeter, I first checked the battery voltage. It was around 3.4 volts. Then I checked the output of the boost converter and it was around 8.9 volts. With stable voltages at the input and output terminals, I charged up the battery for a while using a standard wall charger. After full charge, the circuit is ready to be used. Once the battery was fully charged, I attached the battery to the main board using 2-part adhesive. With the adhesive dried out and with everything coming together quite well, I must say the build turned out to be pretty compact and sturdy. Now it's time to put it in its enclosure. With the battery and the PCB being held in place securely by 4 M3 screws, it becomes easy to insert or extract the module in the future should a need arise. Testing a component with this device is easy. It has 3 pins marked 1, 2 and 3 on the ZIF socket. You can insert the component between any of the 2 pins in case of a 2-pin component like a resistor, and all the 3 pins in case of a 3-pin component like transistors. There is also a footprint for components in SOT packages. All you have to do after that is to push the button and it automatically identifies the pins and thereby the component as well. It also displays a basic specification info for that component. It can identify and measure resistors, capacitors, inductors, BJTs, both NPN and PNP, diodes, MOSFETs and potentiometers. As far as my testing goes, it was not able to detect voltage regulators, crystals and components like that. It was able to measure inductors as low as 0.01 millihenries. Anything below that, it was recognizing as a resistor. During my testing, I also noticed that it has some sort of self-calibration and diagnosis program built into it. It can be initiated by shorting the 3 pins 1, 2, 3 together and pressing the button. Before the test begins, it instructs you to keep a capacitor greater than 100 nanofarad in your hand. Then it prompts you to insert the capacitor. Once that is done, the calibration procedure completes and a success message is shown. After working with this component tester for some time, I can't help but wonder how it does what it does. I wanted to know more. So, I did a bit of research on the internet and learned that it is actually the result of genius work done by 2 gentlemen named Markus Frejek, who originally designed it and later improved by Karl-Heinz Kübbeler. I have included the links to the work done by both these gentlemen in the description. These articles have great resources on the subject, its software, and detailed manuals. If you are interested to know more, please go through these links in the description. These Chinese boards are just a clone version of the original design, and I think credit needs to be given to the original designers for their work. With that, we come to the end of today's video. If you liked the video, please press the like button. Please subscribe to my channel by pressing the subscribe button, and do press the bell icon to get notifications for the videos I upload. Please share the video with friends, and until I see you next time with another video, remember, engineer, experiment and educate.